Our next presenter is the awardee in the field of science. It's Dr. Alessandra Corsi, who is an associate professor in the Department of Physics and Astronomy at Texas Tech University. Dr. Corsi uncovered a multi-sensory exploration process of our universe, where gravitational waves tell part of the story and light then completes it. Utilizing data from both gravitational waves and light now allows scientists to create a comprehensive picture of the cosmic collision that occurs between neutron stars from hundreds of millions of light years away, and allows us to study previously unexplored phenomena of the universe. She has established herself as one of the youngest and most promising leaders in the world in the emerging field of multi-messenger astronomy. And I, for one, have a faith that if we could ever better understand how the universe was formed and where it's going, we can also figure out how to sustain life and make life better on this insignificant planet called the Earth. So with that, I'd like to call Dr. Corsi up for her presentation.
Thank you very much. Okay, thank you so much. I am greatly honored to be here, and I wanted to thank TAMEST for giving me the opportunity to speak. I would like to talk about what is really an historical event, and it's called Gravitational Wave GW 170817, because it occurred on August 17, 2017. This was really this mashup between two neutron stars. Neutron stars are some of the most exotic objects in the stellar graveyard. You can get them by packing a mass larger than the mass of our sun in a region which is 10 kilometers across, the size of a city. And it happens that when they are in a pair, in a binary system, and they orbit around each other, in their dance, they emit gravitational waves. And with this event, it was the first time that we were able to detect those waves directly. And that was not the end of the story. In fact, when the two neutron stars smashed with each other, they released matter, and so they created a cloud of neutron-rich debris and a jet, which you see there in an artistic representation in magenta. And from that jet, we received light. So this is called the first multi-messenger discovery in gravitational waves and light, because we were able to join these two cosmic messengers. And I hope to convince you that this is like studying the world around you by using both sight and sound. So in order for me to really highlight what is so important about joining gravitational waves and light, I'd like to remind you that astronomy is different from other sciences. In fact, it's an observational science. It's very hard to take stuff you want to study and bring it in the lab. You can't certainly bring a neutron star in your lab. And so what we've got to do is use messengers, use signals that are emitted from these faraway objects and bring the information to us that we want to collect. For sure, the most ancient cosmic messenger is optical light. We've used it with naked eyes observations of the night sky, even before Galileo pointed the telescope to the sky. And light itself, it has a broad range of frequencies in reality, not just optical. And we use all of those frequencies to gather information from those faraway objects. In fact, today I will highlight my role in this discovery using radio light. In fact, if you look at the optical sky, it looks very, very different from the radio sky. So the optical sky is made of stars and galaxies. Those are hot, thermal emitting objects. If you look at the radio sky, it looks very different. It's made of objects which are non-thermal, stuff like supernova remnants and quasars. And it turns out that if you can study one single astrophysical event using all spectrum of light, you can learn a lot more. So with GW 170817, we were even more lucky than that. So we weren't just able to use light at all wavelengths to study it, but also gravitational waves, this new type of cosmic messenger. The big deal about gravitational waves is that they are very weakly interacting with matter differently from light. They don't get scattered or reflected, and so they can bring to us information from the densest objects in the universe, such as black holes and neutron stars. I want you to focus for a moment on those frequencies that are indicated at the bottom of that figure there. The frequencies of the waves that we study on Earth, the gravitational waves we study on Earth, are a few hundred to a few thousand Hertz, and so they fall in the audible regime. What this means is you can convert them into sound, and that's why we like to think of multi-messenger astronomy combining light and gravitational waves as an exploration of the universe using both sight and sound. Now, in order to get a little bit more of a grasp of what exactly gravitational waves are, it helps a lot to just think about gravity as Newton's thought of it. And so in Newton's view of gravity, gravity is a force for which every body attracts every other body. So it's the same force, really in a fascinating way every time I think about it, that lets an apple fall on the ground on Earth, or that keeps the planet in orbit around the sun. The force is directly proportional to the two masses and inversely proportional to the square of the distances. And so if you think about it, the problem that comes up is, if this force is an attractive force between all bodies, then how can a body know at each instant of time the positions of every other bodies out there in the universe? This is called the problem of action at a distance. And Einstein, in his theory of general relativity, beautifully solved this problem by thinking, for example, that a planet orbiting around the sun is orbiting the sun not because a force is pulling it towards the sun and so it's bending its trajectory, but rather because it follows a natural path in a curved space-time, the space-time being curved by the mass and the gravity of the sun. So in this view, then, if you introduce this concept of space-time, you can think of ripples on that space-time, just like ripples on the surface of a pond, and those are gravitational waves. And what they do is they bring that information about the position of those objects, and they carry it across the universe. So a gravitational wave is generated every time a mass is accelerated, and so changes position. And gravitational waves spread that information across the universe, which was not easy to explain in Newton's view of gravity. Now, the big challenge is that the gravitational wave amplitude, or h, in that formula is, in general, a very tiny number. While it is true that every mass accelerated generates gravitational waves, the proportionality there is big G gravitational constant divided by c speed of light to the 4th power. All you need to know is that that is a tiny number. And so you really need big masses and violent phenomena, such as 2 neutron stars mashing with each other, in order to generate a wave amplitude that we can actually detect on Earth. The detection is achieved via interferometers that are instruments that look like this. They're L-shaped detectors. Each arm of LIGO Livingston, LIGO is the Laser Interferometer Gravitational Wave Observatory, is 4 kilometers long. And LIGO consists really of 2 detectors. There are 2 twin detectors. One is in Louisiana and one in Washington State. And Italy also has an operational detector called Virgo with 3 kilometers long arm. So the way in which these detectors work is you fire a laser into them. You split that laser beam in 2 and send it in the 2 perpendicular arms. You put mirrors at the end of the arms, and you reflect back that light. And you recombine the light from the 2 different arms in an output photodetector. So that light creates an interference pattern. And what it means is usually we keep that the dark fringe. So if there is no gravitational waves, light in the 2 arms has exactly the same path. It recombines, and we see no light in the output photodetector. If a gravitational wave passes by, imagine a gravitational wave that is coming orthogonally to the plane of the screen, it stretches and compresses the arm alternatively. So it creates an effect similar to what is shown in this simulation in a circle of 3 masses. So it's stretching and compressing those arms, and so it changes the interference pattern in the output photodetector. In simple terms, it was dark when there was no gravitational waves, and when that gravitational wave goes through, now we start seeing sunlight there. The key point is that because we said those amplitudes are so tiny, the relative arm difference, that stretch and compressing that the gravitational waves are causing and that we have to measure, is tiny. And so we're talking about relative differences of something like 10 to the minus 21, meaning you're trying to measure an arm length difference, which is a fraction of the size of an atomic nucleus, over a scale of 4 kilometers. And that is why the detection of gravitational waves is so challenging. Now that I hope I've convinced you that joining gravitational waves and light is the way to go. I'd like to show you what exactly the LIGO detector saw and what light we saw accompanying the event. So in the bottle panel, what you're going to see is what we call a time frequency map of this event. So it's just showing you how the frequency content of that gravitational wave evolved over time. Imagine these two neutron stars, they're dancing around each other, they come closer and closer and closer, and the gravitational waves they emit have a ramping up in frequency, like a chirp. So you're gonna actually hear the sound from that because we said we can convert those frequencies into sound. As the two neutron stars smashed each other, then matter was emitted in the interstellar medium, and so we're going to start to see in the top panel light, and in particular gamma rays from that event, and you'll hear a ding sound when that happens. So let's see if this works. That's the gravitational wave track. The whoop is the merger. And the ding there that plays, that has nothing to do with conversion of sound. It's just for you to focus on when the gamma rays come up. And I'll play this again just because it's fun. Oh, wait. Let me play this again. OK, I will not play that again. But that whoop, when it arrives at the highest pitch, that's where the two neutron stars smashed each other. So, oh, thank you. And then the gamma rays up here. OK, so after this, obviously, there was something very important, which was the detection of the gravitational waves enable us to understand where from the sky this signal came from. And it was particularly important that we had more than one gravitational wave detector listening to this sound. Here you see a map of our sky, that sphere, and the dark green area there is the localization, so where the detectors thought this event came from in the sky. It was an area of 28 square degrees, which means it could fit more than 100 full moons, so still pretty big, but astronomers are ambitious, so every astronomer, I would say, with an optical telescope started mapping that area, because if we found gamma rays, then we said light has a spectrum of frequencies and we wanted to catch them. So the first hunt was for optical light, and sure enough, 11 hours after that smash up, what you see there, that big dot is the galaxy that hosted this event, 130 million light years away. And then that little dot that wasn't present 20 days before that merger is the optical counterpart of that smash up. Here you see a beautiful HST, Hubble Space Telescope image. That's the host galaxy. That's the optical light coming from the smash up. And in the insert, you see how it faded away over the course of a few days. So what we learned from all this, it's a bit beyond my specific area of research, but I just want to mention that what we learned from the optical counterpart was that neutron stars mashups actually enrich the universe with most of the elements such as gold and platinum that we love here on Earth. So next time you look at your wedding ring, certainly think about your sweetheart, but also think how cool it is that it probably came from a mashup of those two neutron stars. I want to take a few minutes to just highlight more my role in all this. When we learned that there was optical light, we were obviously on the hunt for radio light. And this is an image we collected with my group with the Very Large Array. This is one of the most sensitive radio telescopes on Earth. It's a photo here. It's an array of 27 radio dishes. It's so iconic that you've probably seen it featured in the movie Contact. It's Y-shaped, and what we did is we stared at a portion of the sky waiting for a detection, for something to show up. The big dot you see there is the radio emission from the host galaxy at 130 million light years away. That is an unrelated radio source, and in here you see superimposed an image taken on September 1, where there's nothing, and then an image taken on September 7, where a new dot of radio light appeared, and that is the counterpart of that smash up. So we had to be patient. We had to wait 2 long weeks before the radio showed up. But luckily, the radio was also the last to leave the party. In fact, we have followed this event for more than a year after this mashup. And what we've learned is that the event didn't just enrich the immediate surrounding of it with neutron-rich debris, but it also shoot out a jet which is racing through the interstellar medium of something like 97% the speed of light. And the cool thing about it is that this jet was, for the first time, observed slightly off axis, meaning you're not looking down the jet, but you're looking at it from the side. And so we were able to follow how the radio emission evolved during time. In fact, it moved in the sky, as you can see from this map, but the artistic rendering gives you the idea better. As it expands, we can see how it evolves over the course of 150 days. And that told us that those jets are much more complex than we had previously. So I'd like to conclude by saying that the stellar graveyard, which is represented here in terms of solar masses of objects such as black holes up here or neutron star down there, is something that is really open to new discoveries. We've seen only one event, GW170817, in both gravitational waves and light. And we need to study how those various populations are related, particularly, for example, if there's a mass gap between neutron stars down here and black holes up there. And so we look forward to many more discoveries. And I'll conclude with this, and thank you for your attention.
I'm not really qualified to ask a question. I'm John Cook, Houston Methodist. I'm a cardiologist, biologist. I just was fascinated by your talk. One thing that puzzled me, though, was that the whoop.
Yes.
The whoop occurred before the flash of light.
Yes. So the whoop.
And I thought nothing traveled faster than than light. You've got a gravitational wave that you're appreciating prior to appreciating the light coming from that smash up.
Yes. So indeed, so gravitational waves travel at the same speed of light. And so what you're seeing is there are these 2 neutron stars. They're dancing around each other, so they are accelerating masses. And that's where the gravitational waves come from. So the gravitational wave is telling you those 2 neutron stars are changing their position. They're coming closer and closer and closer. And so as they spiral in, they go faster and faster, and that's that whoop that you hear. So you're hearing like the last few minutes of that dance before they crash with each other. And then after they crash, because neutron stars are dense but still made of matter, they spit out some matter. That matter interacts with the interstellar medium, and so only after that you see light.
I see.
So light is not emitted in that process. You couldn't probe the last dance, if you like.
Thank you.
Okay.
Hi, Alessandra. Thanks for your talk. Can you tell us some more about the prospects of finding more merging neutron stars in the next 5 to 10 years?
Absolutely, yes. So LIGO is actually taking data right now. And by the way, you might have heard in the press, was yesterday, 2 days ago actually, that there was one other system, 2 neutron stars smashing up with each other. And it's really cool because it's a heavier system than we have ever found. But in general, the prospects is that we expect, over, let's say, 2021, something like that, to reach 5 times the distance that we've reached when we were observing GW170817. So that would mean something like 40 events per year, of which now we have only 1, 2, but the second one wasn't accompanied by light. So we are expecting certainly to build a larger sample, and that's where we can eventually answer that question of, okay, the stellar graveyard, how does it look really? We just have this one that we've explored in both gravitational waves and light, but we should get to tens per year. So
I have one challenge for you.
yes.
I have a historical interest in this subject, even though I'm not an astronomer. I happened to hear in 1967 or 8, Robert Forward, who had built the first attempt to do a gravity gradiometer, and in fact he had it in his backyard out in Pasadena, California, and people thought he was crazy because he wanted to hear the first chirp, which you played for us.
Yeah.
And I didn't understand, frankly, what he was talking about at the time, but I remembered at UCLA getting a lecture from that. But I've since become a fan of Tycho Brahe, who during the 1500s visually saw the first binary collapse. It's now called Tycho, of course, as you know. But it seems like the popular description of this phenomena, there's a role there, I think, where you could kind of put this in someone needs to put this in a popular astronomy historical context if they haven't already done so. This event is awesome, that the LIGO measurements that you're referring to, and I think it'd be very motivational for young people to see this in kind of a historical context and understand, particularly Robert Forward spent a healthy fraction of his life trying to make this measurement in the late 60s, and I don't know if you're familiar with that history or not, but I would suggest you might want to spend some time, if you haven't, to make a popular, accessible astronomy history of this
yes,
subject.
there is some material, but probably not in the direction you're suggesting. So I will certainly, report back to the huge LIGO collaboration, whose merit is really in this, and give them some idea. There's a lot of work in outreach on their website, but certainly this is a great suggestion. Thank you.
Do we have one more quick question?
Quick question. Roderick Pettigrew from Texas A&M. Beautiful, very interesting presentation. Given that neutron star collisions is a stochastic event, and that this occurs many light years away,
Yes.
How do you time your interferometer measurements? Do you have this running continuously?
Yes, excellent question. Yes, these interferometers are recording data continuously for the period in which they are operating in what we call science mode. So everything is stable and calibrated. And so right now, for example, they're on as we speak. They have moments when, for example, I remember LIGO Hanford site, when a military truck comes by, now maybe they can lose lock, and so we have to go back. But yes, we record them continuously. And regarding the stochastic process that you're mentioning, indeed, one of the prospects, we're not there yet, but one of the prospects is not just to catch this event. So this event, 130 million light years, is relatively nearby, okay? And so there's definitely prospects for trying to capture the noise from the ensemble, all of the other neutron stars, binaries that should be out there, but they're too far to be detected as one single event, but they could be detected as a noise, so a stochastic background. So that we're not there yet, but certainly what you point out is something that is enabled by taking data continuously and then trying to analyze them to see if we can hear that hiss.
Thank you, Dr.
Okay, thanks.